How to model action semantics, and finally get that smarter, sexier action language you've always wanted. Hi, my name is Starr, and today I'm here to talk about the design and benefits of a new executable UML action language. It's still in the works, but fast approaching an initial public beta. An action language is that component of an executable UML model that lets you specify the precise computations a system must perform, regardless of what platform it is implemented on. I'll be using the elevator case study as my running example, and here we see that there is a requirement involving computation. For this case, the 6th floor must be selected as the next stop. The natural language is platform independent, but as we modelers know, natural language is not unambiguously executable, so we need a language built on executable primitives. Historically, action languages have either tended to overspecify, infusing design details that constrain or complicate implementation choices, or they underspecify, in which case they leave too much unsaid, and the implementers have to make guesses that lead to dangerous bugs in the resulting system. Taking a fundamentally different approach to action language design, I think I've managed to thread that needle. For those of you unfamiliar with Schleyer-Meller modeling, let me put that in a nutshell for you before diving into our topic. These days, the big modeling picture is referred to as MBSE, which means Model-Based Systems Engineering. As the name suggests, its intent is to specify an entire system and typically uses sysml as the primary notation. But sysml is not geared towards specifying the gritty details and logical architecture of a software specification, but it does accommodate the inclusion of executable UML. Executable UML is focused on specifying the necessary data, logic, constraints, synchronization, and overall behavior of the software within that system. The Schleyer-Meller variant of executable UML yields specifications that are not only executable, but they are platform independent. This is possible because the modeling language relies on math and logic to specify essential data, synchronization, and computation without making any assumptions about implementation. So when you go through all the hard work to build and validate a model, you don't need to redo it as the platform technology evolves. You might also want to ensure that identical behavior is present on multiple platforms, for example, if you're benchmarking. A software system consists of one or more domains. Each domain represents a distinct subject matter, which may or may not be modeled. For each model domain, we establish our level of abstraction by capturing all of the semantics, relationships, logic, and data within a single class model. We then characterize the life cycles of the semantic elements using platform-independent synchronization rules. These rules are described in a video on my YouTube channel that I'll list at the end of the talk. Finally, we define the computational elements that operate on the data we defined in the first step, synchronized by our state machines. Historically, we're pretty solid on these first two facets. It's this last one where we tend to fly off the rails. The work I'm doing is within what I call the Blueprint MBSE ecosystem. Rather than thinking in terms of a monolithic tool that you might license, we chain together a number of small, focused modeling apps contributed by the modeling community based on a common metamodel. All data exchanged in the toolchain is human-readable text, so you can get everything done using your own favorite editor or IDE. Core elements such as the metamodel repository and text-based tooling will always be open source. And while the underlying machinery will be sufficient to get the job done, there's nothing to prevent the layering on of a glossy user interface that you might license, or integration with existing MBSE tools. So now let's see how we build a model, complete with our new action language. The model entry workflow starts by creating a pair of text files for each class or state model. One file describes your model, and the other describes how it is laid out on a diagram. The markup language for each model type is intended to be human-readable and easy to edit, so there's no ugly XMI or XML here. The XSM file on the left defines the executable state machine with its states, events, and our transition, can't happen, and ignore event responses. The MLS, model layout sheet, is what the flatland diagram uses to convert a model into a nicely laid out diagram. It uses a spreadsheet layout system so that you don't fuss with points or pixels. And we place these text files under configuration management just like code, with changes to the layout always separate from changes to the actual model. Now we take a look at how we organize an entire executable UML software system. At the top level, we define a system package which consists of multiple domains. Each domain may be broken down into subsystems. In our example, there's only one subsystem, so the domain and subsystem share the same name. Within our elevator management subsystem, we have exactly one class model as an xcm file, along with a YAML file giving us a mapping of each data type to a corresponding metamodel database system type. We'll have a lot more to say about types later on. We also have subfolders describing the action language and our class methods. These are organized by class. There's a folder for all of the state machines and another folder for all external entities and their associated operations. Not shown are the model descriptions, as I haven't yet specified a good system for organizing these, but rest assured there will be strong support for integrated documentation in this structure. The elevator case study, by the way, is maintained as a GitHub repository with an associated wiki. I'll have a slide pointing to all those resources towards the end as well. To do anything useful via automation with the model, we need to get all this into a database. But before we can even consider that, we need a schema for that database. And we create that schema from the metamodel of our modeling language. I modeled the Schleyer-Miller semantics using a set of interconnected class models as subsystems within a single domain. This then is a metamodel of our language and is maintained on GitHub and documented extensively in its GitHub wiki. The whole thing consists of about 25 subsystems, each containing a single class model. There are no states or actions since the modeling language itself has no behavior. And I'll just open all the subsystem folders since each only contains a single class model. As you might expect, there are subsystems for the domain structure and the class and state model facets. The class model is captured in the yellow subsystems with state machines in pink. Notice that there are quite a few action semantic subsystems there in the green area. We need to convert this model into a database schema, and then we can load the resulting database with user models such as our elevator case study example, which has its own GitHub repo and wiki. The repository is created by an app called RepoMan. RepoMan sucks up all the XCM files and converts them into a database schema. For the database, I decided to use Andrew Mangonia's excellent TickleRal, with the RAL short for Relational Algebra Library. Once you've learned how relational theory actually works and enjoyed the pleasure of using nested relational functions, it's really hard to stomach SQL. Unfortunately for us Python programmers, Andrew builds all his goodies in Tickle, which, to be fair, it's mostly C in a Tickle wrapper as far as I can tell. Fortunately, every Python interpreter has a built-in Tickle interpreter. So I coded up a Pythonic interface called PyRal. A key benefit of TickleRal is that it takes all those identity and referential constraints that I put in my models seriously. It outputs incredibly helpful diagnostics, which I've used to fix errors not just in the metamodel, but in the metamodel populator. This has been particularly helpful and saved a ton of time in finding errors in my action semantics models. RepoMan outputs a text file serialization of the database and a file full of Python named tuples corresponding to each table. Those named tuples facilitate the metamodel population in the next step. Oh, and TickleRel will also serialize your metamodel out as an SQLite file if you want. Ooh, now we get to the fun part. Our goal is to load that modeled elevator system into our empty metamodel. Fortunately, there's an app for that. Well, an app currently in progress. This is the populator. It loads the metamodel and then rips through our system package, populating the content into the metamodel. Each file is parsed and validated to ensure the model is internally consistent. If any of our database constraints are violated, exceptions will be raised. If all goes well, you end up with a valid model in the repo. Turns out this is easy enough with the class and state models. Populating the activities, however, is a bit more challenging. Action language is a bit trickier because, well, you have to start with your activity written in Scrall. And Scrall is now a full-fledged language with intricate syntax, nested expressions, data representations, and such. The parser is built using the Arpeggio Python package, and this processes a PEG grammar. This yields an abstract syntax tree which is still Scrall specific. The populator walks this tree doing the usual store and validate cycle with the repo to ensure consistency with the other model components previously populated. For example, a name referenced in the action language must be resolved to a defined attribute, flow label, type name, etc., much like resolving symbols in a code compiler. In the process of population, all vestiges of the Scrall grammar are replaced by action semantics. This means that you could input any non-Scrall action language you like, as long as it provides enough information to output the semantics. And I don't see any reason why you couldn't reverse the process and convert the semantics back into the language of your choice, as long as that language has the ability to express the defined semantics. Of course, all of this rests on our ability to define the action semantics. So let's dive into that. There are at least two ways that an action language can go horribly wrong. One, you try to keep the action language too high level and user-friendly, and you end up with ridiculously limited capabilities, leading you to envy a real programming language. The other is that you enrich your language to the point that it is sort of a real programming language, but not quite. To avoid these failure scenarios, we need a clear vision of what exactly we need to accomplish and draw some hard lines on what we don't. And most importantly, we need to completely separate the syntax from the semantics. We're looking for one set of semantics and at least one language that can be parsed into those semantics. An action language's goal is to express a computational requirement by accessing and processing the components of our model. Let's take an example from the elevator case study. In a certain state, a cabin must find the closest requested stop or floor calling in the same direction as its current service direction. We can't use the natural language statement because we can't execute it. Neither can GPT whatever because the statement itself is ambiguous, incomplete, imprecise. So we're going to need a set of executable building blocks that we can string together to express our requirement. We must be able to execute them, and just like our class and state models, the resulting actions must be platform independent. To do this, we don't want to define some kind of high-level, whatever that means, programming language with implementation-specific features. Python already exists. Overspecification is what happens when we go beyond our requirements and specify aspects of the implementation. Two areas where this is likely to happen are in the sequencing of execution and the processing of intermediate data. Let's start with the overspecification of execution sequence. In most programming languages, we assume that lines of code execute one by one in a roughly vertical sequence, unless we explicitly invoke a concurrency mechanism like a thread, process, go routine, or whatever is available in the language at hand. And this pattern of execution is perfectly sane in an implementation where much of the time a small set of CPUs, sometimes only one, is executing the instructions. I can't imagine how I would debug my Python code if all my statements suddenly decided to run concurrently. But our models are platform independent and impose no restrictions on concurrency. In systems like medical devices, fighter aircraft, autonomous vehicles, and such, the real world rarely sequences itself for our benefit. So as modelers, our null hypothesis is that everything could be happening at the same time or in an unpredictable order unless we have an explicit sequencing requirement. Multiple elevator cabins can be simultaneously going up and down servicing floor requests, but a single cabin must close its doors before moving. Or an autonomous vehicle must come to a complete stop before proceeding into an intersection regulated by a stop sign. Now, these two examples of real-world sequencing would likely be modeled with synchronized state machines and not action language. But the same platform-independent reasoning does apply. Consider these two computations. We can see that the execution order doesn't affect the results because they're so simple. But a more complex variation might not be so obvious. Now, these next two statements must be sequenced. Why? Because there is a data dependency. Now, it is perfectly okay and quite convenient to write the actions in a text editor in vertical order, just as with code. But in our action semantics, we need to specify only the essential ordering. We leave it to the programmer or code generator to choose the degree of concurrency best suited to the platform. And we can do this by graphing out the underlying data dependencies. Here we take a look at the data flow graph for the activity that gets executed by an instance of cabin when it selects its next destination. Any given action may execute as soon as each of its inputs have been enabled. Actions are represented by ovals with interconnecting data and control flows. Certain inputs, such as the identifier of the executing instance, input parameter values, or instances of classes, have no source action and are considered to be immediately available upon invocation. Once an action executes, it enables its outputs. A decision or switch action enables only one flow in a set of mutually exclusive outputs. Each action may execute only once, and if dependent on a decision result, possibly not at all. In the case of a synchronous activity, such as a class method, a return value is seen as a final output flow. In this case, a possible next destination floor is output. The purpose of this graph is to ensure that we specify only those sequences of computation demanded by the system. I've drawn this by hand to illustrate the concept, but in practice we write actions as linear text and then derive the graphs as we populate the metamodel. Oh, and don't worry about all the colors and symbols, we'll get to that shortly. And the other area where we can overspecify is in the way that we access and propagate data. This means that we will need platform-independent definitions of our flowing data. We already have these definitions built into our class model semantics, but we need to preserve them as we compute intermediate results. We'll proceed with a concrete example. Our exploration of action semantics will center around the ping method defined on the cabin class in the elevator case study. This activity expresses the requirement that a cabin chooses a next destination if one is available when it is idle using certain criteria. This method is invoked by a state transition outside the scope of our presentation. Our activity takes a single up or down direction value as an input parameter representing the search direction, either above or below the cabin, and returns the selected destination if one is found. In our example, we will search above the cabin in the up direction. Our first statement obtains the set of all accessible shaft levels serviceable by the cabin instance invoking this method. A shaft level is a physical shaft-floor intersection, but an express cabin might service only a subset of these. We call a serviceable floor an accessible shaft level. In our example, the cabin can go to all the floors, so all shaft levels are in effect accessible shaft levels. So we need to traverse the class model from our local cabin instance to all of its associated accessible shaft levels. We'll use the traverse action semantic, which starts at an input instance set. In this example, we submit the single instance executing the method, which happens to be our cabin instance. The circle indicates that the input in this case is the executing instance, and consequently a single instance reference. Here's the path leading from the input instance set to the destination class. The stick arrow and blue flow color tells us that this data does not vary at runtime. It's hard-coded into our action language, so we can think of it as model time data. Here we have the set of accessible shaft level instance references resulting from the traversal. The double arrow indicates that this set could have any number of instance references, including 0. Note also that we have named this flow. Scrall provides a syntax for describing the semantic as shown. Note that the left-hand side is simply the name of the output flow. So we don't use the term variable in Scrall. We just call it an output flow. The intention to assign an unlimited set of instance references is indicated with the double dot assigner. And here's the path. Since the path starts with a slash, it is assumed that it originates at the executing instance. As promised, we're going to be careful not to overspecify data. Instance references are a case in point. Fortunately, our class model gives us everything we need to reference any instance in a platform-independent manner. Every class has an identifier consisting of one or more attributes. If we supply a value for each identifier attribute component, we're guaranteed to obtain 0 or 1 instance of the class. An identifier is denoted by the I symbol in the curly brackets. So a reference to an instance of accessible shaft level is simply a tuple specifying a floor name and a shaft ID. Since our cabin instance is related only to those locations within shaft S1, we have 9 instance references in our example. We're dealing with sets here, so there's no implicit ordering in the flow, and it is perfectly legal to flow an empty set. Our action semantics distinguish single and multiple instance flows. Unless there's some reason you are absolutely sure to never end up with more than a single instance reference, always use the multiple instance flow. When you select an instance of a class using only its identifier, we know that at most one instance can be found, and we can highlight this fact with a single instance flow. In fact, the model populator checks this and instantiates a single instance flow in the metamodel whenever it detects a situation that guarantees no more than a single instance. Any input that takes a multiple instance flow can also accept a single instance flow, but not the other way around. The traverse action is defined in its own metamodel subsystem. It is defined in terms of its input and output flows, and the model time data, which in this case is a path consisting of multiple relationship hops. The bottom half you can't see breaks down the minimum information necessary to hop each leg of each kind of relationship. Like the traverse action, every primitive action is defined in the metamodel devoid of any particular action language syntax. Now let's take a look at a combination of actions a little further downstream in our ping method. Our goal here is to obtain a set of floor names requesting either up or down service as defined by our method's search direction input parameter. We'll start by traversing from the set of accessible shaft levels in that labeled instance flow output by our previous example. We hop from these instances across R49 to get all related instances of the floor service class. Among those instances, we want to select only those calling in the search direction, which happens to be up in our example. A select action applies a restriction condition consisting of a set of criteria. In this case, just one. We see the criterion laid out with all those blue arrows since it is expressed directly in the action language and doesn't vary at runtime. The only runtime inputs are the floor service instances and the requested dir parameter value. Now we have a single floor service instance. The project action extracts a value for each input instance for a set of designated attributes. Its output is a table as indicated by the prongy flow. Think of the prongs outputting horizontal rows if that helps. But in our example, there happens to be only one instance and hence one row in the output with a single attribute. In the action language statement, we use the table assignment operator to clarify that the calling floor's output flow is a table and not an instance flow. As you may have guessed by now, I am using orange for the object-oriented actions and purple for the pure relational actions like project, restrict, join, and so forth. But you might be wondering why we have a mix of object-oriented and relational action primitives. So let's take a quick sidebar to discuss the application of relational theory in our particular version of executable UML. Unlike most UML variants, a class in a Schleyer-Miller class model is not meant to be some vaguely high-level placeholder for a Java or C++ class. This approach is problematic in that 1, there is no systematic way to distinguish high versus low-level details, and 2, the presumption of a class is not platform independent as the system doesn't really care if the code is object-oriented as long as it works. When we model an elevator cabin as a class, we're establishing a set definition. We're saying that all cabins in our system are all bound by the same policies, behavior, and are characterized by the same data. We're not saying anything about the implementation, but we do need some kind of executable foundation, something our action language can manipulate. We need some kind of platform-independent data structure. For this, Schleyer-Miller applies relational theory. This has nothing to do with SQL or databases. The theory itself is simply a branch of mathematics built up from function sets and predicate logic. And if you read our book Models to Code, you won't see anything about relational databases or programming language classes in the embedded C generated from our models. So to make our data executable, as well as platform independent, we think of each class as a relational variable, or empty table if you like. Instances of a class are simply tuples or table rows. This means that our actions and data flows must ultimately reduce to relational operations and tabular flows. But don't worry. For the actions we use most of the time, the relational magic is built in and you won't even notice it. You won't need to specify a bunch of joins, for example, just to hop across a series of relationships. But there are times when you need to correlate data from disparate parts of your model that just aren't directly related. Rather than jumping through awkward relationship traversals, you might take advantage of a simple join and a set operation to get the job done. In fact, we do this in our elevator method example. Now we're ready to take a closer look at how we manage all the data flowing through an activity. Once again, we rely on established theory. The approach to data types I am using is based on C.J. Date and Hugh Darwin's work on types in relational theory. They basically say that types are orthogonal to relations. We apply relational theory to specify relationships among our data, rules, and constraints of the world we interact with. Types define what the data actually is. In our case, types define our attribute and parameter values, and we access those with data flows. Our highest level distinction is between what the relational folks call non-scalar and scalar types, so our actions convey data in corresponding flows. The components of non-scalar data are transparent to our actions. We can apply our standard relational operations such as restrict, project, extract, join, and so forth to view and manipulate the data. Instance flows are typed by class, so in the elevator example, we have seen a cabin flow and an accessible shaft level flow so far. We haven't seen any table flows yet, but we will soon. These are used for conveying intermediate values from class data and are typed by table headers, which are just attribute scalar type pairs. Scalar data, on the other hand, is opaque to our relational operations. We just see a single value which could possibly have many hidden components. Types like timestamp, GPS coordinate, airspeed, and video image are all examples of scalar types, and we'll soon see how arbitrarily complex scalar types can be defined. In the meta model, we define a type as either class, table, or scalar. We think of an instance flow as flowing instance references, but in fact they're just flowing a table whose header happens to match the identifier of some class. In this example, we have an aircraft instance flow which conveys a single column table with a row for each instance reference. We think of the table as having a header component and a body component. In this example, we use the intersect action, which accepts two instance flows of the same type, aircraft in this case, and outputs the intersection as another aircraft instance flow. Here we see the data flowing in and the data flowing out. So yes, it is possible to flow the empty set. The scroll, by the way, looks like this with the output flow on the left of the instance assignment operator and the input flows in action on the right side. We can use table flows to communicate intermediate results when we apply relational operations. Here we want to take the union of our calling floors obtained in a previous example and all stop floors resulting from a button press inside the cabin. Each flow is typed by a temporary table. We name this table by concatenating the attribute and type names with underscores. So the non-scalar type named floor underscore level name is just the floor attribute and its scalar type, level name, squashed together. Both tabular flows coming into the union operation must have identical non-scalar types, and they do. The union gives us the sixth floor since there is both a floor call in our search direction and a stop request there, and the eighth floor which only has a stop request. So the output of union also has to match the type of all the input. If you look closely, you'll see that the floor.name attribute in our class doesn't match the corresponding floor attribute in our intermediate table. So we need to insert a rename operation between the class population accessor, flow F11, and our join operation. As a convenience, all relational action primitives will accept either an instance or a table flow. In the case of an instance flow, it is implicitly converted to a table flow whose type matches the complete set of class attributes and types. And here we rename just one of those attributes so we can do the join. Our resulting flow is a table whose type reflects that we have two columns with our desired floor names and heights. And you can express all this in Scrall on a single line as shown. Each attribute of a class takes on a set of values defined by some scalar. Let's take GPS coordinates as an example and see what it takes to define it. First of all, we have the type name. Next, we expect it to have two internal components, latitude and longitude. Each of these components inherits a base type of rational restricted to a range. Even though these are not relational types, remember that it is our job to specify and not implement. So we don't specify a platform-specific data type like float, for example. There should also be a number of operations supported by the type, such as DMS, which converts the latitude and longitude to degrees, minutes, and seconds, or distance, which could be provided as the subtract operator. Date and Darwin also define a THE operator, which can return a single component such as the latitude of a location. Finally, a selector is an operation that returns some element of the type set. This could be a named element such as North Pole or just a literal value. You might even designate a default selector to be invoked when none is provided. For some types, you may want to specify a precision that must be supported on all platforms. So a scalar is defined as a type name, a set of assignable values, and a set of operations supported on those values. The big question is, how do we incorporate all this into our meta model? And the answer is, we don't. Type theory is its own subject matter, and there already exist many typing systems. The Schleyer-Miller method itself has little to say about how scalars are defined. Consequently, the details of type definition are considered beyond the scope of the Schleyer-Miller metamodel. That said, we still need a way to refer to the type names, and our action semantics must be able to invoke whatever type-specific operations have been defined. As the metamodel populator encounters references to scalar and operation names in the action language, it can consult the type definition domain to verify that corresponding names and signatures are defined, and raise an error when they are not. This way we can write action language with full support for non-relational types. There's a lot more I would love to cover regarding the modeling of action semantics, such as control flows, but we're short on time. So let's just sum up what the metamodel must include for any given action. For any given primitive, we must define any model time information. Earlier, we showed a snippet of the specification required to define a path. That's 16 classes right there. But also we need to model the required input and output flows. I find it helps to sketch out a specification for each action as part of its documentation. Here's one for the select action. Here the restriction condition is rather involved, so it is indicated by a data store which expands out in yet another document. And here is one of the relational primitives. Note that I didn't make it up. I just copied it out of Date's book and integrated it into our data flow concept. All of those relational primitives are defined in the relational action subsystem. To design and implement an action language, you're going to need a few things. First of all, you need a set of action semantics and ideally sound theory for defining them and binding them together, completely independent of your language. Check. Next, you need a clear set of principles for the look and feel of your language. For Scrall, I wanted to highlight the subject matter and de-emphasize the modeling artifact, so I decided to start by making names related to the subject matter as readable as possible. Rather than going the traditional programming language route where long names get jammed together, a name is simply one or more words separated by spaces. The price to pay for this heresy is that you can't have any keywords, or at least very few of them in the language. In place of keywords, Scrall uses keyboard symbols. To keep that from getting confusing, symbols are carefully chosen to resemble what they do. 2 dots indicate multiple instances. An arrow sends a signal, with the @ sign indicating the time. A hash symbol sort of looks like a table. 2 table symbols join 2 tables. Question mark's a decision, that sort of thing. Oh, and don't worry, you can still use underscores in names when you need them. Another principle is that operations should nest and combine exactly as you would expect in any mathematical expression. The target of a signal action is an instance flow, so you can use any expression here that yields an instance flow. And any expression that yields a time or duration can appear after the @ sign. Of course, you should always use well-named intermediate flows when it makes the action easier to understand. Efficiency is not a concern since the implementation is free to eliminate superfluous flows. Scrall has no concept of a for each statement. Instead, we just apply operations to sets. To demonstrate this, I need to present a quick one-slide tutorial on the select action first. This action takes an input instance flow, applies one or more criteria to each instance in the input, and outputs a subset of the input instances. Here we output all instances of the local aircraft flying above a certain altitude. We use a comparison criterion which compares an attribute of the input set against a supplied scalar input. In this example, we use a ranking criterion instead. Here we use the rank operator, which orders all altitude values from lowest to highest and then grabs the set of instances with the highest value. We can specify a desired cardinality of 1 to ensure that at most 1 instance is returned. Note that we adjusted the assignment operator to represent a single instance output flow. Tutorial over. Now we're ready to look at the real example. Now let's look at a more interesting example. Given an up or down request at some floor, we want to determine which cabin can get there fastest given its current workload. It turns out that we've already defined the estimated delay method on the cabin class, which takes a floor and a direction and computes the estimated duration to service that request. We can use the rank criterion to get the shortest duration, but instead of comparing an attribute value, we can invoke our method instead, since it does return a scalar value, just like an attribute. And so we can solve this problem with a single line of Scrall. Now you might be thinking, wow, you're just making it hard to read by squashing it all together with your weird terse language like that. So let's see what it looks like in a more verbose action language. Here's an OAL, Object Action Language solution, which relies on for each iteration. So I have to ask, does the verbosity of this keyword-rich language help you understand the requirement better? The whole spaces in names thing and the fact that I'm not designing a richly featured programming language made me decide against an LALR style parser and instead choose a PEG parser. I find it a bit easier to write and manage a PEG grammar as opposed to the BNF style. I chose the Arpeggio Python package to handle the grammar specification, parsing, and generation of the AST. Here is a snippet from my grammar. It is a switch statement with a tuple flow assignment inside each case block. You can see I'm also using that rank criterion in my selection actions to pick the closest or furthest destination from the elevator cabin. The Schleyer-Meller variation of executable UML lets us build specifications that are platform independent and executable. This is possible because of our strong mathematical foundations in each of the model facets. To specify platform-independent actions, we use data flow graphs so that we don't overspecify sequence, relational semantics so that we don't overspecify data processing. We define action semantics in the meta model independent of any particular syntax. Design the syntax as part of your action language and make sure it supports a subset of the action semantics. Finally, here are a number of resources if you want to dig deeper. I hope to issue a 1.0 public release of the MetaModel Populator along with Scrall in the first quarter of 2024, along with a major new release of Flatland. If you're interested in integrating your existing tools, contributing new tools, or otherwise supporting or accelerating this effort, please get in touch.